So here's practice problem 4 on page 476, and this gave a lot of people problems, so I thought I would work it out. So what they said is that, well, I'll read the problem. It says an object with a charge of 7.5 times 10 to the negative 7 coulombs, that's this one, is placed at the origin. The position of a second object with a charge of 1.5 times 10 to the negative 7 coulombs is varied from 1 to 5 centimeters. Draw a graph of the force on the object at the origin. So obviously this thing's going to get pushed to the left, Q1 is, by Q2, but I want to create a graph for this. So here's what I'm going to do. I'm going to do it at 1 centimeter, 2, 3, 4, and 5 centimeters. So let's set it up. The force that pushes them apart is Coulomb's law. So that's going to be K Q1 Q2 over R squared. Okay, that's going to be the magnitude of the force. And now, if you'll notice, these are the things that are going to stay the same. So let's figure out what those are, and then we'll divide them by 1 centimeter squared, and then 2 centimeters squared, 3 centimeters squared, and we'll make a little chart, and then we will graph it. So this is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. That's the electric constant. This tells us that electrical forces are very, very strong. Times Q1, 7.5 times 10 to the negative 7 coulombs. And then this is going to be 1.5 times 10 to the negative 7 coulombs. And then we're going to divide this by whatever R is, and you need to make sure that it's in meters, and then you're going to square it. So what we'll do is we'll put 0.01, 0.02, 0.03, 0.04, and so on in there. But let's figure this out and just do it once so that we don't have to type it into our calculator over and over again. So the force is going to be equal to, well, here's my calculator. So this is going to be 8.99 times 10 to the 9 times 7.5 times 10 to the negative 7 times 1.5 times 10 to the negative 7. And we're going to figure that. And so we get this, 0.001011. I don't know if we want to carry this many. We'll just carry all of them for right now, because 375. Now what are the units for this? Newton meter squared, because the Coulomb, these two coulombs cancel the Coulomb squared here, so leaving Newton meter squared. And then what we're going to do is we're going to take this number and divide it by the distance. And the first distance is 1 centimeter. 0.01 meters is 1 centimeter squared. So you just divide that by 0.01 squared. And very unsurprisingly, I get 10.1 newtons. And notice the meter squared cancels the meter squared here. So now I'm going to take that same number and divide it by 0.02 meters squared. So 0.001011.375. I don't need all those digits, but divided by 0.02 squared. And I get, well, not surprisingly, I get 1/4 of that, which is 2.53 newtons. So this is at 1 centimeter, this is at 2 centimeters, and then we'll do 3 centimeters next. So I'll just go, so that's going to be 0.03. And let's see. And you get 1.12 newtons. Notice it's getting less and less. I'll tell you what, we'll skip 4 and just do 5. And we get 0.405 or 0.41. Now if I want to graph this, one, two, three, 4, 5. So this will be x in centimeters. And then this is going to go roughly to, so we'll just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I didn't do that very well, did I? Oh, well. So 2, 4, 6, 8, 10. These should be the same. If you're using graph paper, it's a lot easier. And this is force in newtons. Look what we get. At 1 centimeter, we get 10.1. At 2, we get 2.53. At 3 centimeters, we get 1.12. There's 1.12, be about right like there. And then at 4, or at 5, I skipped one and went to 5, it's 0.4. And look what I get. I get this inverse graph. But it's inverse, it's 1 over r squared. Now what's the force going to be as I approach 0? It's going to approach infinity. Of course, you can't get two charges to exactly be in the same spot for that reason. But this is what the graph looks like. And that
is all.
Is problem 4. And, say it, Simran.
That is all.